All right, hello everyone. So today we have a question from Calculus 2, where we're finding the area outside of the circle r equals 3, but inside the cardioid r equals 2 plus 2 cosine theta. So if you can look at the picture above, in red is the circle, and in blue is the cardioid, or something like to think of it as like a heart. Kind of looks like a heart, right? Anyways, we're looking for that region that you see that's shaded in. That's the area that we're looking for. And similar to maybe what you learned in Calc 1, we're going to set up an integral where we take the difference of two functions. So if you recall from maybe your first semester calculus class, you would find the area between two curves by subtracting the curves, the largest minus the smallest in some form or fashion. Same thing here. We're going to do the same, the largest minus the smallest. And you would have something, let me just show you the formula that you would have. You would have something such as what I have down here, b and alpha, and we'll get a little more into the formula in a second of why that is, but yeah, it's going to be an integral between two functions which we're taking a difference of, and this would be b, the beta and alpha. Those are your two angles. Okay, and you might say, okay, two angles of what? What are we speaking of here? So let me go back to our original picture up here. When you're asked to find the area between two curves, you always want to kind of consider between what and what, between two angles is the property in question, or question that we have valid for. So in this case, it's from where these two curves intersect. I'm going to take an integral that goes from the first point of intersection to the second, okay? And how do I figure that out? Well, you're just going to set them equal to each other like I have here, where we have 3 equals 2 plus cosine theta. And go ahead and solve for that. You would get 1 equals 2 cosine theta, and one more step is cosine theta equal to 1/2. And if you look at the unit circle, whatever you need, there's multiple answers for this. There's like pi over 3, there's 5 pi over 3, there's minus pi over 3, etc. There's an infinite. We only need a couple though. And which ones am I going to use? Well, I'm going to take a look at the picture. And as I have written here, you're going to get, you're going to use minus pi over 3 and pi over 3 for your limits. Why is that? Because when you're setting up your limits of integration, they need to be in order from smallest to largest, okay? And there's a bit of wiggle room around that, but we're not going to go over the wiggle room today. Let's just take that as a general rule here. So you want to go from smallest to largest, and minus pi over 3 would provide that. Yeah, if you had like 5 pi over 3, that's a valid answer. But then I'd have an integral that goes from, you might say, oh, well, you just put your integral from pi over 3 to 5 pi over 3, but that would be all of this stuff. That's not what we want. We want the stuff over here. So that's why minus pi over 3 to pi over 3 works from smallest to largest, okay? So just make a note of that, please. And let's go ahead and set up that integration here. And we're going to use this formula, as I had talked about earlier, which is like, it's an area formula for polar curves, which is based off sectors. And it's 1/2 the integral from alpha to beta of the difference between the two functions squared, where one is larger than the other one. So here, R1 is bigger than R2. R1 and R2 are just those functions. In that, between those two angles, alpha and beta, which are minus pi over 3 and pi over 3. And there we go. That is what our setup would look like right there. And what I would do is I would FOIL the 2 plus 2 cosine theta out and subtract the 3 squared, which is the 9. And you get this expression right here. And what I did from this line to the next, went ahead and used the identity cosine squared theta equals 1 plus cosine 2 theta over 2. And yeah, because you can't integrate that 4 cosine squared, excuse me. So therefore, all of that turns into what you see right here. And you can go ahead and integrate that as such, and then plug in your values of integration, which I'll let you do. Now, we could have also used 0 to pi over 3 and the difference between those two functions. The square of those functions subtracted from each other. And here I'm using symmetry because if you look back at the shape, that region from 0 to pi over 3 is the same as the one from minus pi over 3 to 0. And we use a lot of symmetry here just to simplify things. Don't get me wrong, minus pi over 3 to pi over 3 still works, except you might have to do a little bit more in terms of arithmetic. That's all I'm saying with that. All right, so in general, that's how we deal with finding the area between two polar graphs. You're going to use that formula which I have right here, 1/2 alpha to beta, integral from alpha to beta, r1 squared minus r2 squared. r1 is the larger out of the two functions, and larger here is basically the larger radius, so it's like farther from the origin. So you subtract those two functions and you find where one is larger than the other. Those are your points of intersection usually, from minus pi over 3 to pi over 3. Okay, yeah, I say usually here because there are some cases where this doesn't apply, but you don't really deal with that much in this class. So in general, this is what you'll be working with. Okay, well, I hope this helps. Thank you for your time.